It's a big pleasure today that I can introduce Steve Cousins, who came from the US, the Bay Area, who is the president and CEO of Willow Garage. Some of you may know Willow Garage from the ROS system, the open source robotics, and some of you may know Willow Garage from their collaboration with Google on cloud robotics. I personally believe that these two issues on open source robotics and cloud robotics are probably some of the most promising areas in robotics today. And I believe that if we see ahead, say 5–10 years, we'll look back and say, well, these issues were some of the things that changed the way that we look at robotics. I think it will. So therefore, of course, it's a big honor for us to have Steve with us today. I met Steve just about a month ago or so. We were having a nice discussion at a conference on advanced robotics and its social impact, which Steve is also very much engaged in. But today, I believe that Steve will introduce us to some of the work that you're doing at Willow Garage and the ROS especially. I'm very pleased to invite you to give us this talk, so let's give Steve a hand.
Thank you very much, and it's always nice to start off the talk with a round of applause, because then I don't have to, the pressure's off, right, or whatever. I want to talk about personal robotics, and let me set a little bit of context. So it's weird a little bit to have somebody with a title of CEO showing up in a university giving talks, right? And I've been doing that all week. I do have a PhD in computer science, but I don't use it very much during the day anymore because I'm administrating a little bit. But I'm passionate about robotics, and the company that I have, Willow Garage, is not a traditional company. So a typical company is, especially in Silicon Valley, a startup company, and we're about 5 years old. A typical startup company, somebody gives you money, you make a pitch and you get money, and the expectation is within 3 years, you'll maybe make a profit. Hopefully within 5 years, the investors get all their money back, and they hope 10 times as much money as they put in back, right? That's the model. Our model is a little bit different. We're privately funded, but the funders have asked me to have impact first and worry about return on capital second. Right? That's a pretty big difference. It's not a nonprofit, and the reason it's not a nonprofit is because if we're successful, in order to be really successful, we have to sell products, right? Because if we're not going to sell products, if we give away products, we can only give away the amount of money that we have. If we actually create value, something that people are willing to pay for, then we can actually have impact way beyond the amount of money that we have. And that is similar to the venture capitalists, and we might have a lot more impact. So our mission, to put it succinctly, is to build a new industry. And it's an industry in personal robotics. And I'll talk about what that means, what that implies. So I'm going to talk a little bit about business, and I'll talk a little bit about technology, and then maybe a lot about robotics. In some ways, it's all about robotics. So if you think about an industry, this is what we want, right? I one time put this slide up at an intern talk, and I had the title Business Model, and everybody laughed. Because it's a great business model, by the way, if you can do it. It's not much of a model. But, and this is exponential growth curve, right? And you know that if you wanted to grow an industry that follows this curve, that it's impossible. Because that's going to infinity, and if you consume all resources in the universe, that has to end eventually, right? It would end about right here. So this isn't actually what we want. The reality is something like this. You grow for a while. But what you do want is, you want to be in this part of the curve. Right? Not in this part of the curve. And it's probably not in this part of the curve. Although I would argue for personal robots, we're about like here, right at the beginning. But this, and the business model of Willow Garage is to say, if you think about here, like this line, right? If I can bring the time from here to here in by 5 years, if I can somehow speed that up, that's worth a lot of money, right? It's worth a lot of money because the time value of money, say, $10 billion or $100 billion industry, 20 years from now, it's great to think, oh, it's a $20 billion industry. 20 years from now, it's a $100 billion industry. That's wonderful, but 20 years from now, I'm going to be retired. Right? So I can enjoy it a little bit. And so, and that's sort of classical financial theory. The other thing about this kind of growth curve in industry, thinking of an industry, is that it doesn't often go like this. It often goes a little bit like this, which is that you have linked S-curves, recurring technologies that keep on pushing out. So if you think about Moore's Law, right? Moore's Law, the cost of computation, the cost of a unit of computation goes in half, or the amount of computation you get for the same money doubles every 18 months. And that's been true over a long period of time. But it hasn't been one technology curve that's done that. You had TTL logic at some point. Then you had CMOS chips. Now you have multi-cores, right? We're continuing to get the performance, but we're doing it with different technologies over time. The other thing is that, although I don't think I drew it very well here, the time frames of those different technologies keep getting shorter and shorter and shorter. And a physicist named Geoffrey West made an argument, a parallel argument that I have to evaluate still, but the argument was it's actually required mathematically that you have less and less time at each one of these cycles. Which does beg the question of, as we go from the PC, which took from, say, 1980 to 1995, which is sort of the big growth term of that. And then you have the internet, which went from 1995 to 2000, actually 2001, but it's still going on, and maybe social networking, whatever you want to call the different trends. They're getting shorter and shorter, right? Mainframes lasted a lot longer than PCs, which lasted a lot longer than internet. They don't go away, but the next one takes over for growth. At some point, it's like, I'm going to have another thing next year. That seems like, wow, how can I do that? Then if you do that, the next one has to be only 6 months, right? And the next one's going to be 3 months or something, and that's scary. Okay, let me take you back in time for a minute, and then I'll come back around. Because we're talking about robotics, and so this is a clip from 1966. So I'll talk over a couple of interesting things about this right off. That's Johnny Carson, right? Johnny Carson passed away, but he used to be the late night host that sort of in America, everybody watched Johnny Carson talk about the next day. He's smoking a cigarette on TV in California today. And this is the first industrial robot. And Joe Engelberger is considered the father of industrial robotics. He's showing this off, and he's talking about how the business model that they had, how they were going to sell those for $20,000, $20,400. But if you didn't have that much money, they would lease it to you for $2.50 an hour. And if it worked more than one shift, so they have this human concept of shift. So after 8 hours, they only charge $1.50 an hour. Right? And the whole clip, I'm not going to play all the audio, but the whole clip as they're talking about this is about, the theme of it is, this robot's going to take your job. Right? It's the robots are going to work, they're going to do these jobs that need to be done. Actually, this is kind of fun. He turns it on. You hear the hum? It's incredibly loud.
It takes a little while for it to warm up. Well, it's only a machine. What do you want? You take about 20 seconds to warm up yourself.
Watch right now how fast it moves. So Joe Engelberger should know better than to stand in a workspace. So this goes on, and it's interesting, that particular task, right? There's no perception, right? That robot doesn't have a camera, so it's obviously pre-programmed. And there's no reason why that thing has to do 2 warm-ups. It's all for show. He goes on to have it, to train it in real time about how to direct the band, and then makes a joke about how it's going to replace the band director. And also, in the second year, it actually pours beer into a glass, which is scary because that's one of the demos that I see people doing today with robots. And so, what have we done since 1966? So this is how I think about personal robots. So industrial robots, the robot lives behind a cage in a factory. And there's actually another analogy, which is our machines in the cloud, right? These are servers that live in a server room somewhere, usually air conditioned and power controlled and stuff. And the server rooms live in the cloud, and they live, somewhere where you don't see them. And servers have managed to get out of the cloud. I mean, your PC at home, if you have a desktop PC, is basically as powerful as a lot of the servers that are out there. There's just a lot more of them. And your cell phone, right, has as much power as anybody's laptop had 10 years ago, if you even had a laptop 10 years ago. And so, we're moving along, and computation gets out. Computation gives us a lot of leverage. Robotics, if you get it out of the factories, can also give us a lot of leverage. And that's the bet of this creative personal robotics industry. The bet is we're going to create some devices which can help increase productivity enormously outside of the cages. I talked to one of the executives from Yaskawa. They make the Motoman series of robots. They're probably the most widely bought industrial robots. And he said that there's only so much blind work left. Right? And what he meant by that is, this rote work, like the way he putted, right? You're going to just do the same thing over and over. And in factories, if you go to an auto factory, Toyota plant, your car is about half built completely by robots. And it's the first half, right? The roll of steel comes off, stamp machine just basically stamps the parts. Those parts get welded by robots automatically. And they get, then the whole thing gets painted by basically dipping it into primer, and then robotic arms go back and paint because they can minimize the amount of overspray and the amount of waste. They're much more accurate than people. And then once you get the whole thing painted, now the people come to work, right? And so all the rest of the work is robots aren't good at. They're not good at running wires through cables very well. They're not good at putting windshields in, although there's more and more technology helping. But that's blind work. That's the same robot doing the same thing. In a car factory, a new car gets made every 56 seconds. Right? And then so 56 seconds, and then the next station, every station. It takes 2 days for the car to go from end to end, but every 56 seconds another car comes off. That's the same work over and over, and the kind of work that people do in that is 56 seconds worth of work. Right? I do some job in 56 seconds, do it again. Right? All day long, breaks are built in. That's the kind of work. Now we shift from that model of I'm behind a cage. The robots in industrial factories are behind cages because they're dangerous. If you get, like Joe Eichelberger did, if you get in the workspace, it could actually knock your head off. And now you want to take robots out of there and put them around people. What do you need? Well, you need to be able to navigate around a human environment. And human environments are not fixed the way the factories are. Kids leave toys in the middle of the floor, and you're going to have to go around them. People walk out in front of you, you're going to have to stop. Linked with navigation, its own separate problem, and maybe the hardest problem in robotics, is perception. Right? How do you perceive the world? How do you recognize that this is a remote control? Not to mention, just recognizing that it's a remote control and having some idea of what it might do is a challenge. If any of you could pick this up and figure out how to turn this projector off. Right? I would posit to you that no robot in the world today could pick this up and turn this projector off. Even the PR2, which I think is state-of-the-art, I'll show you in a minute, only has a parallel jaw gripper, and so just picking it up, it would have to use its other hand to push, and these buttons are pretty small. And it's really a challenge. I mean, I'm not saying we couldn't do it, but that's a challenge. And it wouldn't, if we did make the robot use this remote, we wouldn't be doing it by, you wouldn't know about the remote. It would just be some rote actions that we programmed in. And this perception, this is like really hard, right? Because if you aim a laser scanner or a camera at this, if you really look at it, what you're actually seeing, what I see as I look at this, I'm seeing reflections of this and this in the glass. Right? Those things aren't there. It's all reflections. This is a really difficult object to pick up. Even this mug we could do today. Thank God it's got a pattern on it. It's some features from that. But that's where we are. And then last of all, manipulation. So manipulation means basically using your arms to move things in the world. Even if you solve all these problems, there's one more, which is integration. You've got to somehow put it all together. And all of these pieces, especially perception and manipulation, there's different specialists who work. Those are really, really hard problems. And so PhD students do, a computer vision thesis or a SLAM thesis for navigation, or they do a grasping thesis. They don't do all of it together. And so somebody needs to come along and say, let me take the results of all that work, put it into one package and make it work. So I'm going to wind back. Willow Garage is 5 years old, and about 4 years ago, we started a project to build a personal robot. I joined about 4.5 years ago, and this is what I saw. I went to Stanford and I saw this robot. That's Eric Berger, who's one of the inventors of the robot. And here's a robot's arm hitting him, which you don't see robots often doing to people. This is other tasks that it's doing. This is Keenan Weierbeck. He's the mechanical designer, and he obviously trusts the safety of that robot. Now, all of these videos that you're seeing here, this is a loop that they put together before Willow Garage even knew about this robot. All of these videos are being done with what's called eyes on telly, right? So there's Eric usually sitting in a chair with two Phantom Omnis, basically 6-degree of freedom arms that he can push around that measure what he's doing, and he's controlling the arms remotely using the Phantom Omnis. He has a monitor in front of him. You can see what the cameras of that robot are seeing, but he's not using it, right? And he can hear what's going on. As he picks up a Lego or drops it, he can hear that because he's in the same room, and that matters. So you can see this robot's fairly capable, and this is actually why we decided to get into it. We said, okay, here's a robot that seems reasonably safe, that seems reasonably capable. It can even open a beer, and an incredibly lazy graduate student who won't even reach for it. So this is what we started with, and Eric and Keenan had this vision. They said, we want to make 10 of these robots and give them out to research labs so that there's a common platform so that research can advance faster. And the picture that they drew was this one. They said, we want people to be able to focus. Their model, they were both grad students at the time, and their model was that this top line represents a PhD program. Right? You spend a long time doing a lot of engineering, both hardware and software, to get something so that you can do a little bit of incremental work that's your thesis. And can't we shift that? Can't we make it so that you start with a platform and you just have to learn it, and then you can innovate for the rest of your thesis time? Notice that they didn't suggest that you could graduate in 2 years. It is more work. But the point is, think about this as a catalyst in the chemical reaction sense. This is something that will allow you to go from taking 20 years to get an industry off the ground to getting 15 or even 10 years, right? That's the kind of thing that can really speed things up. If you get all the grad students in the world being that much more productive, the technical problem should get solved that much faster. So that was the vision. And what came out of that was this robot that we call the PR2. This is the update of the robot that you saw before, but it's now a commercial product. Right here it's doing navigation. So when we built it, how do you're going to build a robot platform, how do you know it works? The first thing we did was make it navigate around. This is a video for a conference paper about navigation. But we had this robot first navigate 2 pi kilometers. So 2 days in a row it was supposed to go pi kilometers. People ask me why pi kilometers, and the answer is you had to pick a number. Pi. By the way, I should say that. Since I was telling somebody that Larry Page of Google was a classmate of mine when I was at Stanford. So I know the backstory for Google. Google IPO'd for, does anybody remember? $2.78 billion, or in other words, $E-billion. That was a joke on Wall Street that nobody knows. Anyway, so we had the robot, and we taught it how to navigate around. That was using sort of standard known techniques in robotics. We just implemented them in an open source way. And then we taught the robot to plug itself in. Now, plugging itself in is a really cool capability and completely unnecessary, right? If you're going to engineer a solution, you should just build a dock, and the robot should just dock back in and plug itself in that way. But plugging in is something that requires basically millimeter precision of the arm. And so when we first did it, in order to plug in, the robot would go tap in a spiral, trying to find the holes. We'd get close and then tap in a spiral until it felt going in and then it would go in. And as you saw in that little clip, now it goes, basically just looks around, sees the plug, and then just goes pop, right? And so the calibration is another sort of unsung topic in robotics, but an important topic, and one that I think we've got a pretty good handle on now in Ross. So this is a demo that was done as a research program out of UC Berkeley, Peter Abiel's group, and this robot was actually, in this video, was shot at Willow Garage. The student came down. If you're ever making a video in robotics, this is the thing you should make sure you do. When you get done with the towel, you make sure you smooth it like this. Everybody loves it. This robot has like, this video has gotten seen like more than 500,000 times on YouTube, and I think it's mostly because of that. But so Peter's group got the robot to fold towels. We spent a week trying to teach it to play pool, and this is a little clip from that. Made some long shots and some angle shots. The robot wasn't designed to play pool. It was just something that we said, hey, can we do this in a week? At Technical University of Munich, they have one of our robots, and this works with another robot to make pancakes. And this is an example of opening a drawer, getting out the dishes, bringing it over, and then putting breakfast. That's not the way I don't think they eat that kind of eggs in China. But an example of carrying the plate over. And they actually did a big integrated demo where the PR2 went to the refrigerator, opened up the fridge, got out the pancake batter, carried it over. The other robot poured it onto this hot plate, flipped the pancake, and then the PR2 delivered pancakes. And they were able to deliver 4 pancakes in an hour. This is another one-week project that we did called Beer Meat. For those who don't, actually, you guys can all drink because it's Denmark, but in the US we have to call it root beer meat. And here's the robot getting a beer from the fridge. Again, it's sort of manipulating the refrigerator door, closing the door, making sure the door is closed, and so forth. And then it delivers the beer to people. And it's kind of a beer snob robot in the way that they put it together. It'll bring you a Guinness if you ask for it, but if you ask for Bud Light, it says, "Are you sure you want a Bud Light?" So this is another application. It uses the navigation, it uses the arms, it uses the capabilities. It just demonstrates that in a short period of time, again, in 1 week they did this demo, you can get a robot doing some basic tasks. And so that it's not showing off this, it's showing off the platform, right? The fact that you've got a hardware platform that's robust enough and a software platform that's rich enough that you can put together meaningful applications. That, by the way, this is not a robust behavior. They just did that because they thought it was cool. Okay, let me come back to the business side now. That's a little bit of overview of one of our products. I should put products in quotes on this slide because they don't make any money. So on the left side, there's software products. So there's the ROS, the robot operating system. I'll say a little bit more about that. There's a package called Gazebo. Gazebo was written at the University of Southern California along with the Player project, if you guys know Player Stage, and is a simulator that had been kind of stagnant for a little while, and then we started funding it because we needed a simulator, and so we've been using it for ROS and the PR2. OpenCV, if you've done any computer vision, you know about it. It's a computer vision library. It was created by Intel about 11 or 12 years ago by a guy named Gary Bradsky, who was an Intel fellow, or maybe because of this became an Intel fellow. And Intel supported it for about 6 years, and then other needs called, and Gary had left, and so they were sort of funding it was on the decline. And we hired Gary to join our research team, and the first thing he said was, hey, we need to get OpenCV going again. And so the same people, it turns out, who live in Russia, who were working for Intel, sort of creating this toolkit, we now pay, and they continue to do it. And they actually have they're now attracting funding from other companies as well, like NVIDIA and some other companies. So this company in Russia, ITSIS, it's a bunch of mathematicians, PhD mathematicians who like to do computer vision, continue to work on this. And we basically fund and direct the project a little bit to make sure, like one of the things I insist on is that OpenCV comes out in a new version every 6 months, so it's on a reasonable release cycle. And then the last one is the Point Cloud library, PCL. Point Clouds, I'll come back to PCL and talk a little bit more about it. But those are all open source. They're all licensed under the BSD license, which means that it's available for commercial or non-commercial use, which means effectively that we don't make any money on it. Right? We give them away, and that's okay because, again, our mission is impact first, and those packages, I would argue, have a huge impact. I'll talk a little bit more about ROS when we get to it. The PR2 I just showed you is a robot that we sell. It's expensive. Its list price is $400,000 US, so it's not a cheap robot. It's mainly bought by research labs, and we were going to give away 10 of them. That was the original plan. And so we made 20 so that we could give away 10 and keep 10. And then we couldn't decide. We offered, we did a call for proposals worldwide, and we got 78 really high quality proposals. And so we couldn't decide. We gave away 11. We kept 9. And then we decided that since there were so many people interested, we would sell them. So we've been selling them. We've probably now sold a couple more than we've given away, about 12 or 13. And they don't sell really fast because people don't have much money. But it turns out professors moving to new universities often negotiate a startup package, which turns out to be the right amount of money to buy one. We give them a 30% open source discount for anybody who's basically has a track record of open source, because that's our mantra. And so most people buy it that way. At the other end of the spectrum, I'll show you a clip later of a TurtleBot. TurtleBot is for the robot operating system. It's the cheapest, almost the cheapest platform you can get that does something interesting with the robot operating system. It can run the navigation stack. The same navigation software that's running on the PR2 also runs on the TurtleBot. The TurtleBot costs about, I think you could buy one for $1,500. Most of the cost of that is, and you can download the plans and build it yourself for probably $1,000, and most of the cost is a netbook that's capable enough to run the software. And then the tech side is this platform. This is a remote presence robot. That's the camera on the top of it. You see it navigating down the hallway. And here you see, there's a person on the other side of that who's talking to somebody in the room. And this is a really interesting technology, and I think it's going to have a huge impact in the short term. So this tech side, it's called tech side because there's a guy, for some reason his first name is Dallas. And if you know U.S. geography, Dallas is a city in Texas, so we call the robot the tech side. And Dallas coincidentally lives in Indiana, which is another state, which is not California. And when we hired Dallas because he's an electrical engineer, and we tried really hard. We needed to make a small, like this size motor controller board for the PR2. So while we were building the PR2, we contracted with a company in San Francisco who was supposed to be experts in this. Students out of MIT founded it. Okay, they're going to help us make this motor controller board. And after 3 months, they gave up. They basically said, it doesn't matter what you're going to pay us. We're not going to work on this anymore. It's too hard. Okay, that's not good. Because we're kind of depending on this thing for our robot. And so then we tried to find other consultants, and we eventually found this guy Dallas, who lives in Indiana, who was a friend of one of our electrical engineers. They had worked together in school. And we hired him as a consultant, and together they actually got the motor control board to work. They solved the problems. So, okay, I know this guy exists. I know that he's helped us create this thing. And he was good enough that and he was expensive enough as a consultant, that after a while, like a year, we said, okay, we're going to hire him full-time as an employee. And so we did. And now I know that he exists. Because I made this decision to hire the first worker who didn't live in California, in Menlo Park. And so I know he exists, and I met him once or twice when he visited. But otherwise, he's not on my radar, except at tax season, because now I pay taxes in Indiana. But otherwise, I don't know him. And he goes to meetings, and there's a big conference table in the meetings, and he's the guy inside the telephone in the middle of the table. So, and that's a terrible position to be in if you've ever done this, right? You call into a meeting, your voice is coming out, and if I'm, in the meeting, and I say, "What do y'all think?" and I look around the table, and you're all nodding. Dallas is shaking his head like this, but I don't see that, right? And so we did, okay, let's go for it. What? And so Dallas didn't like that either, and so he said, well, can I just have a laptop? Can you just put Skype on a laptop at the end of the table, and then I can be part of the meeting? Which is a pretty good solution. Skype is great if you're using a laptop and talking to your friend, like this, right? If you put it at the end of the table, it's not designed to give you the wide angle to see everybody in the room, or it doesn't actually have the resolution enough to see the board at the end of the table. So it's better in the sense that when we go around the table to see what everybody thinks, you can see Dallas shaking his head and say, what's wrong, Dallas? But you can't, it's not the ideal solution for him. And so he said, see the little camera on top of there, that's a $100 camera from Logitech. He said, can we just get one of those? So we said, all right. So they got a cart, it's like a little cart that they put in the room. They mounted an LCD screen on the top with one of those cameras. They put a desktop computer on it. They put an uninterruptible power supply so that they could unplug it and move the cart and then plug it back in without having to reboot. And so they created this little cart, and they said, and this actually worked pretty well. Dallas could see you, and you could look around now, it's better. And then they said, wait a minute, we're a robotics company. We can do better than this. Right? And so they took one of the casters from the PR2, which is a two-wheel unit that can turn and drive, And they took one of those, which we had sitting on the shelf, attached it to the bottom of an 80-20 frame. 80-20 is Legos for adults, for those of you who don't know. And they put a car battery down low, actually a marine battery, because car batteries will leak at the tips. Marine batteries are a little better. But basically that kind of capacity, lead acid. They put a computer down low. They put a screen like this, speakers, microphone, that camera. There's actually one more camera here that's downward facing with a wide-angle lens. There's 2 laser scanners, but they're not used. We never used them. They were just there because Larry Craig said he wanted these, and he said he wanted a laser scanner, so we put them on. And then they ended up not even buying them. So. Anyway, once Dallas had this, his life and his relationship with Willow Garage changed completely. So before he was the voice at the table, or he was in the electronic engineering meetings, he wasn't in anywhere else in the company. And I still didn't know him. I'd only seen him once or twice. As soon as he had this computer, or this robot, he was driving down the hallways, right? And so I would pass him in the hall. Hey, Dallas. Hey, Steve. Like, that's an interaction that you don't expect to have with a robot, right? He would come to lunch. He would meet, but he would come to lunch and have a conversation, lunchtime conversation. He would come to a stand-up meeting. He would come to a seminar on his own terms. Nobody had to set up a camera for him. In other words, he was in our environment as a full-fledged embodied person. At a table, he's got a seat around the table. And so I believe, and I just like to tell the story because I think that, when we talk about where the industry is going, I think this is going to be a big deal. There's a really clear business model for this. If you have to travel to another place on any kind of regular basis, once you've been there once or twice, going back there is just expensive, right? I'm going to go there, it's going to cost me $2,000, $1,500 to $2,000 US for the trip. I got to pay for airfare, I got to pay for hotel, taxi, meals, all that stuff. And if I can avoid that trip by having a robot there, I can justify paying some fraction of that $2,000 for a robot, right? And so let's say that I'm going to go on a 2-day trip and I'm going to spend $500 instead of $2,000 to get a robot. When you do the math and you say, hey, that's worth $100,000 a year for that robot, right? So I can charge something less than that, and a company can make this robot you guys can make this robot for less than $100,000, right? So if you can solve it, there's some technical challenges around networking and stuff to make this right. But we decided this is interesting. We're going to spin off a company to do this because there's, whenever you have customers who will be willing to pay for something and suppliers who would make money if the customers paid that, that's a good situation. So we spun off a company to do that, and that's why I put it in parentheses on my products list, because it's no longer one of our products. Here's the Turtlebot. Oops. Here's the Turtlebot.
Whether you're a beginner just starting to learn about robots.
Turtlebot is a very small platform that has basically a Roomba for the base. It's an iRobot Create platform. And there's a Connect scanner here in the middle. Connect is really amazing because it's $150. It's got a netbook, and you can put something else on top if you want to. But it's running, you see it's running a navigation stack from Ross. It does people following. Basically, it's a platform on which you can play with Ross. And so if I come back to my slide about how the business goes, I think we're already through the first one of those split curves, right? Roombas are out there. There's 5 million Roombas that have been sold by iRobot. There's lots of competitors in the marketplace. A similar robot is pool cleaning robots. Do you guys have pools here, or do they just freeze? But there's a lot of places in the world where you have little robots that go around and clean pools. But that's pretty much fixed. It's kind of like the blind work in industry. I think the next thing that's going to happen is this remote presence robots. I think the technology is there. We're close enough to there. There's actually a few on the market already. There's one called the Giraffe that's actually being sold out of Sweden. And I think that's going to take off and have its curve. I don't know how big it'll be. But obviously, I think it's something that's what we spun off the company. After that, the next logical step is manipulation, but under human control. Right? You don't have to solve artificial intelligence. You have to let the person do the perception, let the person guide the manipulation, and let the person work remotely. And the interesting thing about these two robots is that they're not taking away jobs. Instead, they're moving jobs. They're letting me avoid my commute. They're letting me live somewhere where I want to live. I always ask Dallas, why does he live in Indiana? I grew up in Illinois, which is next door, and I live in California for a reason. And he said he likes living there, and I didn't understand why, but then he pointed out that his house is like twice as big as mine. And so that maybe explains it. He doesn't know the real estate rule about the 3 laws of real estate: location, location. And then I think, after this, there's the kind of thing that we dream of, Rosie the robot, right? Versatility, automation, autonomy happens later, typically. So let me switch gears for a minute and talk about a couple technologies. So 3D is here suddenly, right? 3D showed up because all of a sudden the video game industry wanted it, right? So the Kinect is available for $150. The PR2, actually, you see it here, has a sensor suite that basically can do the same thing as the Kinect. But the sensor suite costs probably 10 times as much, if not more. And so the Kinect is suddenly interesting because everybody can put one on little robots and suddenly be able to perceive the world in 3D in a way that you just couldn't do economically before. But it also points out something interesting, which is that we as roboticists are the poor stepchild of other industries, right? We don't get to make inexpensive things because we don't have the volume, because we haven't gone up that curve yet. And so we have to depend on the video game industry to come up with a cool sensor that we can then use. Or the computer industry to come up with a cheap computer that can process the images, which we can then use. That's on the hardware side. On the software side, there's the point cloud library that I already mentioned. The point cloud library is basically the software that you need to deal with those point clouds, what comes out of a 3D imager. And it continues to grow. There's about 100 people around the world who are actively contributing to PCL. So although the guy who founded PCL is actually when he was at Munich, we've now hired full time. This is a theme for us, by the way. We hired the guy who did Gazebo. We hired the guy who did OpenCV. We hired the guy who did PCL. We started ROS, but we did it by hiring the guy who did Playware, which came before. And so, anyway, the software here is continuing to grow. It's actually a worldwide community effort. We're just kind of guiding it and investing in it and providing a fraction of that resource. Manipulation side, the big thing coming down the pipe is the grasping pipeline. So this is open source software that lets you, and actually works on, eventually will work on any robot, because we're doing it in a general way. But it's software that lets the robot link together perception, what's on this table, with the arm navigation, which allows me to get the arm close, with grasping, which says, I know to grab it this way and not this way. Or, for this, I know not to, I won't do it here, but I know not to tip it over. So the grasping pipeline is a series of software. It's done by people with different areas of expertise and all put together and integrated. And it's what we have and what's coming down the pike is not the final word in grasping, but it's a system that turns over that you can use to actually do something, and it will continue to get better. And if you have students who are interested in aspects of that, pointing them at it and saying, look, here's a grasping pipeline that's part of ROS. Your part is this thing you're doing, and you're doing algorithm for motion planning. So look at what's in there and make it better, right? And you can demonstrate that it's better, and you can show an end-to-end demo without having to do that whole thing. You do the part that you're good at. Arm navigation is already there. So I haven't talked about ROS yet, but I will in a minute. ROS is the robot operating system. We've been doing it for the last, it's probably 4 years old now, but the first release happened at the beginning of 2010, the first the 1.0 release. And we've been having every 6 months a new major release of it. So the first one was called Box Turtle. They're all named after turtles. And then Sea Turtle, with a C as in the language. And then Diamondback, which actually is a kind of turtle. And E, the one that just came out, is Electric. And in Electric, there's arm navigation. So that was, before that, ROS was about tools and build systems and navigation. And now this high-level stack arm navigation basically lets you do planning. So arm planning, the problem is you have a 6 or 7 degree of freedom arm. If you try to just exhaustively figure out the best path to pick this up, it's an NP-hard problem. Right? So it's not you're not going to get an exact solution in any reasonable time. And so people use stochastic algorithms. There's all kinds of approaches. Probably the most popular approach right now is called OMPL, which is a motion planning library from Rice University in Texas. And what we did was got 4 interns a couple summers ago from the places that seemed like they were really promising motion planning approaches. We brought all 4 interns together. They implemented the approach of their institution, and then we built a common API around them so that you could plug in. So when you write an API from one instance, you may or may not get it right. When you generalize over 4 different approaches, you probably have a good chance of getting the API right. And so we did that, and now that's released code. And so again, it's not the end final word in motion planner, but I think it's an interesting start, and there's workable motion planners in there that you can use to get your robot to move. What's missing, and I was talking about this at lunch, is a framework for sharing controls work. So controls sort of a level down, and that's not particularly well done in ROS. And so you can think of that as an opportunity to contribute to ROS and really make a substantial contribution to robots around the world. The last thing about this is interactive grasping. So we've been spending a lot of time trying to skirt the problem of perception in AI by looking at the continuum between teleop, right, where you just drive the robot directly. It's not so easy to drive a 6th degree of freedom arm, although you can try. And the other end of the spectrum, which is complete autonomy, right? The robot just comes along and picks up the glass, or maybe I say, in English, pick up the glass, and then it does this. I'd have to do this, right, because speech recognition only works if you have a microphone close to your mouth. But there's lots of room in between those 2 approaches, right? There's approaches where you say, I want you to pick this up. I know you're not going to be able to figure it out. Put your gripper like that, right? And it does that. Or even better, I just draw a line and say, I want to pick this up, so I draw a line across here. I'm going to put my gripper orthogonal to that line and pick it up. So those are different approaches, and that's an interesting area because it suddenly says, oh, maybe there is a human behind this robot. Maybe the robot's doing a lot of stuff on its own, but when it needs help, it's not like, oh, I didn't program the last 10%, the hard 10%, right? I did most of this application, and I can't field it because it's not right. Instead, I say, I can field it, and I can ask a Mechanical Turk worker, if you know Mechanical Turk. I ask somebody on Amazon.com who's willing to be paid 10 cents for every image that they recognize. So when I don't recognize that that's a glass, I just take a picture of it and I put it on the internet and I say, what's that? And somebody says, oh, for 10 cents I'll tell you it's a glass. and they'll even draw the circle around the top or whatever you need, and then you can go pick it up. And that was actually used. Peter Abil's group, I showed you the towel folding. The first version of towel folding, it took 25 minutes per towel, which is terrible. But I mean, better than not folding at all, I guess. But it's not going to take anybody's job. Except for one reporter. Reporters always get things wrong, and that reporter said there's 25 towels per minute, which is great. But it was just false. But they did another version of that, which was a version where they said, let's, instead of what they did in analysis, you hold up the towel like this with the robot, and what takes so long was staring at it, all the pixels, until you finally figured out where the corner was that you should grab. And once they grabbed it and they did this twisty thing, then they could go ahead and fold it. Once you get 2 corners adjacent, folding the towel is an easy problem. But getting those 2 corners is tough. So what they figured out was, well, if you pick it up, so the algorithm for towel, in case you're wondering, in case you need to do this, you reach into the pile of towels and you grab something and you shake it like this. Right? When you hold it up, the lowest part is guaranteed to be a corner. Okay? So you grab that lowest part and you let go and you hold. Now you've got a corner. Now the game is, how do I find the other corner? The lowest part is the opposite corner. So if I lay it out, there's 2 corners in the middle, right? I don't know, and I can grab those 2 corners and put it like this on the table, and it's going to be like this. And those 2 corners, one of them goes with that corner, and one of them goes with the other corner. So if you just take a picture of it and you ask somebody which corner's on top of the 2 middle ones, then they'll tell you. Then you can pick it up and do the rest of the fold. It's easy. So they did that, and they got it down from 25 minutes per towel to 3 minutes per towel. Just by basically, they actually sent text message to a grad student who then had to look at the picture and text back. It's kind of annoying, but that's what they do with grad students. Sorry if you're Chris. Okay, so the robot operating system has been growing like crazy, and I'm not going to talk a lot about the details of ROS. I'll just tell you one story. So I mentioned milestones at the beginning about we had the robot navigating as we were trying to get 10 built. We had the robot navigating for, eventually we did 140 kilometers with the plugging in together. So the robot was totally untouched for 140 kilometers. We called that milestone 2. Once we got through that continuous operation phase, we said, what we need to do next is get the software that's going to ship with this robot as we're trying to finish the robot. We're going to get the software in a state that people can use it. And at the end of 2009, I interviewed all of our summer interns, there were about 20 of them. I always do exit interviews to see how's the program, what can we do better. And one of the things that they said, that every single one of them said was, the software's terrible, it's unstable, I spent all my time trying to get bugs fixed and I couldn't use it. They were able to work because they were at Willow Garage, all the engineers were there, they could go ask somebody if they had the problem. But it was not a state of software that we wanted to ship. And so we basically called a halt, stop developing software. For 6 months, just improve what you've done so far. So we had this thing where we've been all throwing in all kinds of capabilities. Stop. Let's make sure that there's a tutorial, that there's unit tests, that there's documentation for everything. And that when you check stuff in, all those tests are going to get run all the time. So we stepped back and we did that. And that software engineering made a big difference. And once we had that, and we sent, in 2009, we sent those grad students back and they all started talking about the code. And then in 2010, students came and they actually got a good experience, and these things started growing. And so, and again, 2010 was the 1.0 release, so all that stuff was kind of leading up there. This is ROS repositories. It's interesting that it's even that high in 2010, since we hadn't released it. But people around the world were starting to use it and create repositories and contribute to it. And this actually is out of date. The current number of packages is around 3,000. So the great thing is there's 3,000 packages in ROS. And the horrible thing is there's 3,000 packages in ROS, and you can't find anything. And that's the problem we're working on now, is how do we use social networking tools to let you know which are the ones you want to use and which are the ones you want to avoid. The other thing about the robot operating system is that it's not just about the PR2. Here's the PR2 at Penn playing some music. But here's another, this is the robot I mentioned doing pancakes at Munich. It's running ROS. It's using KUKA arms and shook hands, I think. This is another robot that's running at the University of Pennsylvania. It doesn't look like a robot exactly, right? It's a quad rotor, but it's running ROS. Here's another plywood robot out of Stanford. And this one's actually evolved now into a sheet metal robot. But it's a robot arm that's running ROS. That's now with a laser scanner running the ROS navigation stack. This is the Carobot out of Germany. This is a pipe checking robot out of Zurich. This is a car running ROS, an autonomous car. I think this is out of, I don't remember which one that is. I don't know why anybody would put ROS on a surfboard, but somebody did. And most interestingly, when I was in Zurich, so it's in Paris, this is the TurtleBot. When I was in Paris, I saw the thing I'm going to add to this video, which is a rat running ROS. They have a robotic rat with whiskers that runs ROS. So this is a robotic architect. So it goes on and on. There's lots of robots. And the point of this is, ROS is a general purpose tool that you can use for lots of things. There's going to be a ROS conference. So ROS is about 4 years old now. And in 2010, we had the 1.0 release. So in 2012, right after the ICRA conference, there's going to be ROSCon 2012, which we're excited about. They just picked the venue last week. But let me tell you why I'm convinced that personal robotics really has something to do. There's a whole bunch of open questions about taking jobs and increasing productivity and where that leads the world to. But this is a guy named Henry Evans who is, he was a CFO of a Silicon Valley company until he turned 40, which was about 10 years ago, when he had a stroke, right? It can happen to anybody. Henry had a stroke, and he can move his head now after a lot of rehabilitation. So his wife's there reading letters off of a board. She watches where he looks and she picks the letters. He can use that same technique to type. So he's moving his head, the camera's tracking where his head is, and you can see his thumb has a little tiny bit of motion that he can use to click the mouse. That's the amount of input that he has. He saw this clip on CNN, that's Charlie Kemp from Georgia Tech, and he contacted us and said, hey, I really want to work together with you guys because I think that robot will make a huge difference in my life. And so we started this project, and this is a control panel he's using to drive that robot to make it do things. So the first thing he did was have it pick something up off the table. That's what we thought would be cool. The next thing, he turns around and he takes the hand of the robot. This is actually a later clip, but he took the robot's arm and he moved it right up by his face, which scared us, right? We're holding the run stop going, ah! but he wanted to scratch his face. He has an itch. He said he has an itch 3 or 4 times an hour. The next thing he wanted to do was shave himself. Now, we measured, actually the Georgia Tech guys measured the forces that he's using on his face, and they also measured the forces that his wife uses on his face. And they found out that it's an order of magnitude difference. He pushes 10 times harder than his wife does, which is why he wants to shave himself like that. Here's him looking at the map of the building, and he's in another room where he can't see the robot. So remember we talked eyes on teleop with the PR1. Here he's doing eyes off teleop from another room, and he's using it to pick up things and put them in a drawer. Because in his house, he's the neat one, right? There's always one of us, or sometimes none of us, that's a problem. But if there's one of you who's the neat one and the other one's less neat, it's really frustrating if you're the neat one and you can't clean up, right? And so here Henry gets pushed down the hall in his wheelchair and he sees something he wants to put away, but he can't do it. With this robot, he can be able to do that. And the last thing which I think is interesting is that we've been talking a lot with Henry. He came, I should have put a clip in about Halloween. We had him at Halloween giving out trick-or-treats using the robot to kids at a mall, which was really exciting. I mean, for 10 years he hasn't been able to participate in that, and suddenly he's able to go out and do it. At this Christmas, I'm going to take him shopping. Means that I might just take the robot and leave him at home and he can call in, or he may come along and work the robot nearby. But either way, he's going to try to interact with malls if the malls will let us. And then he's going to give his first tour of Willow Garage in March. We've scheduled that with the students from Stanford who are coming by to get. They're in a class on technologies for disabled people. So we're trying to push him along. That direction of him interacting with the world, not just manipulating things, but interacting with people through a robot, is one that surprised me. That's what he's really interested in. When I ask him, what is it you most want to do with the robot, he says, I want to do a comedy routine. It's not that funny. I read it. I read the script. But it's interesting. So, okay, let me stop. I have a couple more things, and then I'll stop the question. This is, I got roped into being the ICRA Challenge Chair. ICRA is the robotics conference next May, and so I decided we should do something interesting. So this is 2 simulated envisionments of what we want to do. We want to create a little sushi restaurant with a table that's actually rotating, because I think that's a hard problem. And we're going to ask the contestants, you send your robot in autonomous mode, and it's supposed to first clear the table of dirty dishes and put them over where the dirty dishes go. Then go to the place where the clean dishes are stored, pick them up and set the table. That's because somebody said setting the table is a hard problem, so I thought we should throw that in. And then the third thing is something that was suggested by Kuka, which is to pick up things off of a moving table and then go put them onto the table. So like sushi, when you buy it at a restaurant, you pick up the plates and you bring them over. You get charged by the number of plates. Here you get points by the number of plates that you bring over and their value. So plates with a QR code on them are worth the least. Textures worth a little more. Lambertian plates are worth a little more. And glass plates are worth a lot. Right? Because we know that hard to do. And we'll just see how much you can do. There's a variant of this, which I call hide and seek. It's a challenge for robots, which is just outside the room, you show the robot an object, then you go in the room and you put it on a table somewhere, and then you go out and you say go, and then the robot has to go find it and see how long it takes to bring it back, if it can even do that. It seems like a really easy problem, right? It's a really easy problem to say, and I think it's a little bit beyond the state of the art. I put together a couple of wish lists. I gave a keynote at an electrical engineering chip conference called Hot Chips. And I said, these are the things we need. We need more battery life, always. We need great sensors, because it's hard to justify developing sensors ourselves in mass quantities. We need fast, especially wireless communication, because we'd love to do stuff in the cloud, but if you have an autonomous robot running around, it's going to go over wireless. The chip's called Hot Chips. The conference is called Hot Chips. I said we need cool chips. Right? One of the things about the PR2 is a little bit noisy because you're trying to cool down 16 i7 and A1 cores. We need less wires because one of the things that fails most often in robots is wires and connectors. And we need hobbyist access. So if you're developing new chips for some industry, give access to hobbyists, give access to roboticists, so that we can use the things and try them out and push on the state of the art. I also gave a talk to robotics community at the ISRR, and I said, well, the number one thing that we need is low-cost, capable arms, because the arms on the PR2, if I sell one at retail, it's about $100,000, and that's basically the cost of making it. The KUKA makes the lightweight arm that they got out of DR in Germany. That arm costs retail about $180,000. Arms for robots are really, really expensive today, capable arms. And you can't make robots that are going to help people like Henry, and where the whole robots can end up costing $400,000 or even $200,000. We have to get the price of robots down to $20,000, which means that the cost of building an arm has to come down to under $2,000. And that's a huge challenge. I was at one of the labs this week, and they were showing me this cool carbon exoskeleton for an arm. And the exoskeleton cost $10,000. No motors. Right? And so that's a challenge. We need people to release code with papers. Right? We need to be able to share code. We need to be able to validate each other's experiments. This is science after all. And that's something that hasn't been the case in robotics. We tried to sponsor a best code competition. It's difficult. It requires changing the entire way the paper process works. When do you submit your code? If it doesn't compile, is the paper rejected? We need architectures for tactile sensing. There's some work going on in this area, but there's a lot more work to do. And because there's no widely available common tactile sensors, there hasn't evolved or hasn't become sort of a de facto standard for architecture for how you should do that. And I always ask, by the way, what's a robot? My working definition is technology anthropomorphized, but you make it different. Okay, let me just end here. So I started by giving you this picture of the problems, and my take on the problems and sort of the ROS, the Robot Operating System story, Willow Garage story, is that navigation is solved with our navigation stack. By the way, when I got into robotics 5 years ago, the first thing that everyone told me was that navigation was solved. And it's been a few years and no one thing is solved, but well, that was solved, right? For integration, my story is that it's ROS, and ROS continues to grow both in size and I think it's actually working. In perception, there's an object recognition package that lots of people working on object recognition. In ROS, the state of the art right now is something called the textured object detector. And I tried this. I would say it's at a level that even a CEO can run it. So I had to connect on a tripod, connected to this computer, but moved into Linux instead of Mac OS. And I hold the connect above here so that it learns that this is a background pattern. This is just two posters that we take together. It's poor man's turntable. Right? And then you take one of these objects. I actually scan this object. I put it on here, and I run the next part, and I circle it around like this, and it builds a model of that object. I did that for 2 postcards and some kind of bottle that I had at home. I did this at home in a terrible setup. I had the connect here, and this here, and I had a lamp here, which if you imagine how the light goes, there's some great specularity bouncing off of here. And I trained on those objects in that bad way, and then I put them up and aimed to connect at them, and sure enough, it starts saying, that's that comic, that's that comic, that's the bottom. And so, I'm not saying it works in all situations. I'm saying I could do that at home with a setup that we basically just downloaded off of that you could download as well, and connects are cheap, and so you could try it. And so that stuff is not released yet, but it's available but not released. Released means we've done some kind of quality control. This is stuff that just finished at the end of October. But I think that there's again something that's turning over that we can improve. It's coming along there. On manipulation, there's the grasping pipeline that I already talked about. But in between those, there's human in the loop, which I think gets us a long way to being able to field robots and get robots into use sooner. So that's my take on where we are with robotics. And I know there's a lot of other things I could have talked about that I left out. So let me stop and let you ask any questions.
So I think that we can just take a few questions.
Okay.
I have one for you. Now you didn't. We didn't go too much into the cloud robotics stuff, but nevertheless with the ROS, so we would imagine sometime in the near future that a lot of the processing will happen over a connection. Now, while at the same time you're interested in some of these social aspects, and there will be people who don't have network access, and will have places where the network access is not very good.
even in Denmark, if we travel an hour away from Copenhagen, a lot of places you don't have a good connection, Wi-Fi connection.
Yeah.
So what happens in these situations? Even if we go ahead 5-10 years, there will be some point where we will be relying that all our processes are running on the cloud, and we have the physical robot running, and we have security issues that it's in the home of the whatever disabled or the elderly, and it's running, and suddenly there's no connection. What are your thoughts on these things?
I think there's a whole bunch of questions in there. The connection to the cloud is interesting because you want to be able to use that processing as you need it, but you're going to have to craft the problem carefully. The PR2 has 7 cameras. We actually got to Connect standard now, so that makes it 9 cameras, plus 2 laser scanners. The amount of data that's being generated by a PR2 every minute is just going to overwhelm any wireless connection and cost you an arm and a leg to process in the cloud. So that's why we decided to put a lot of processing on board. But there's this trade-off, and it's an engineering trade-off. You have to figure out maybe we won't solve object recognition on board because we can just send a few images. We don't have to send all that data, but we'll send a few images. We pick out the right ones and send them off to the cloud, and they'll do object recognition and send it back. I think that's plausible. You might do the same thing with motion planning and some of the other computationally hard problems. So that's one, but the trade-off there is, like you say, if you don't have a connection to the cloud, then the robot's totally disabled. And we actually have this problem with the tech side. The tech side is driving around the building. Cell phones are really good at going from one tower to the next automatically. Wi-Fi is not designed that way. And so what happens is you'll get to a Wi-Fi dead spot. It might actually be within reach of an access point, but you were talking to that one over there, and as you move away from it, it gets bad and suddenly you fail. And you don't, the algorithms don't give up on that one until it actually fails. And then they take about 30 seconds to say, oh, well, there's one right there, to reconnect and keep going. So solutions to that, that's one of the things that has to be solved for the tech side to be successful. But that's only one example, right? So there's going to be times when you're off the network, and if you get stuck in a Wi-Fi dead spot where there really is no Wi-Fi, and you're relying on the cloud, then the robot's just dead, right? And dead robots in your halls is not pretty, right? They take up space, and it starts to be a mess. And then they run out of batteries, and then you have to push them home. So it's just not good. We have experience with this. We have a lot of robots in the building. So I think some autonomy actually gets you out of that problem, right? If you have the ability to do some processing on board, going down the hall, network drops out, we just keep going because I know that over there is going to be good network again. Kind of like our ability to go from one restaurant to the other without that. So that's the second part. And then the question about the sort of social implications and the use of robots in the third world, I think is really, really interesting. And it's not going to be a PR2, in Africa or in Calcutta, right? It's going to be some other technology, and doing laundry for somebody, which might be a great task to put a robot in a home here, is not going to be the task that somebody in the third world needs first off, right? They need clean water, or they need food. They don't need somebody to do their laundry for them. And so that's the challenge that I think, we were talking this morning about modular approaches where you build hardware that is appropriate to the situation. You build a toolkit that allows people to construct the solution to the problems that they have. I think that's a really promising approach, and that's pretty much what ROS is about. ROS is a software toolkit that lets you run on all those different types of robots and put together things that work. Right now it takes a programmer to do that. At some point we'd like to get it to where a high school student can take some components and some software and put them together. One of my dreams is that in 10 years, somebody who's disabled and has some unique disability, somebody who they know, like a niece or a nephew or something, can say, "Oh, I'll make a solution for you." The same way that if you have a problem, a mathematical problem or a modeling problem, somebody can say, "Oh, I'll make a spreadsheet for you that'll help you do that," or "I'll make a web page for you that'll help you solve that problem." We've got tools, and the tools are pushing down to where many, many people can use them to build custom solutions. And that's something they talk about called the long tail, right? The ability to make exactly the solution that you need. And we're seeing that. That's a trend that's going to be important over the next 15 years. Not only software and hardware pieces, but 3D printers are getting really cheap, right? You can buy for $1,000 a little printer, a MakerBot. You have to put it together yourself, but it'll print 3D objects. And we're actually using them for prototyping at Willow Garage now. We finally decided to buy a big 3D printer, but for a while we just were using a MakerBot. And I thought about getting one, for my kids for Christmas. It's a little bit expensive, but it's in that price range. You can imagine it. So, I think another 5 years, and you're going to have a $200 MakerBot. That's like a laptop or an iPhone or something else. And so people will just have one. And when something breaks in your house, you'll download the model of it and you'll print a new part. That's it, right? And, I mean, seriously, companies that send you parts, that's just going to be just, you go online, pick the part that you need, download it, and they don't have to hear from you. So it's a great incentive. So anyway, that's kind of where I think those are going. Yes?
You have named human in the loop in the connection between perception and manipulation, or what was it meant, rather more largely? Because I wonder, what is your opinion, or what do you envision when it comes to using humans to teach robots? How do you see it? The government projects?
Wow, so human in the loop is a theme for us. It comes in a lot, right? So TechSci is all about human in the loop. Although, you characterize it as using humans to solve problems, and I think of that as like Dallas is solving his own problem, right? By using, it wasn't that the robot was using him to solve some object recognition problem. He's using the robot to be someplace it can't be. And I think people will use robots to be someplace they can't be and manipulate things. If you think about the TechSci is a disabled individual, right? Dallas is perfectly able-bodied when he's in Indiana. But when he's in the TechSci in California, he can't even open a door, right? Now he can cause a door to be opened. This is amazing what you can do socially, right? He bangs into the door and somebody will open it. And he actually went and got a screwdriver for a technician in California, which you think, how could he do that? He just drove, he knew where the screwdriver was kept. He knew what screwdriver exactly he wanted. He drove there, he asked somebody who was nearby to get that screwdriver and put it on his base, and then he drove it back. And so the technician was continuing to work on the robot, and he was able to bring the tool. That's pretty amazing for a robot without arms, right? And so mind-bending to think, oh, you don't have to do everything yourself, you can cause things to happen. Nevertheless, it would be nice to have an arm on the TechSci. It would be nice for him to be able to open doors himself and be more independent. And so I think of that as how the human in the loop works. Then the last case is where you say, well, I want this work done. I don't want to do it, so I want a service to do it. And some combination of a robot that I either buy or lease, plus a person that I pay or the lease pays for, causes the work to get done. And that's very much like paying somebody to clean your house or wash your car, whatever you do. Yes?
There are a lot of robotics labs around the world doing different things with their own robots. But we don't seem to be very good at working together, experimentally speaking at least. How do you see that fitting in with open source platforms for robotics?
So I think it's getting better slowly. The trick is that the research community is small, and so building a business selling robots to the research community is not a good idea if you're interested in the business, right? And so there's been a number of companies over time that have done that, and when they have, the community has advanced. So it's good for the community for there to be a common platform. It's just not good for the business, right? And so, we're in a fortunate position that we can continue to offer PR2s, even though we're kind of making a loss on the program. But we offer them because I think it's good for the community to have that common platform. Not everybody can afford them. The turtlebots are out, so people can use those. It's not just us. There's a company called, I guess it's Robotis, has their new Darwin Op platform, which is a little servo bot that's about this big, that's somewhat robust. Aldebaran in France has them now, also being sold into research. So there are some common platforms. I think it's important for both things to happen. It's important for the hardware to evolve, for students to build robots from scratch and learn how to do that. Some students, right? Somebody's going to have to know how to build the next generation of hardware and overcome the problems, either cost reduction or increased capabilities of the platforms that are offered. But it's also important that people who are working on the software side have a common platform so you can share results and compare. And we've tried to do that as much as we can with PR2. There's only about 35 PRTs in the world, but they're at a lot of top research institutions in robotics, and we're starting to see a lot of sharing. We're seeing people either typically sharing at the code level, right? So that's why ROS is growing, because people are plugging into it. It grows on lots of robots, but in particular the PRT community benefits a lot. And some people buy PRTs because they say, well, I want to be part of that community, I want to be able to share that code. So I think we're getting there, but it just takes a while.
Okay.
Great, thanks for that.
Let's thanks Steve once again. And then I will encourage you to stick around, because just outside we have some beers and wine and soft drinks and a bit of snacks, and have time to have a chat with Steve when he's here with other colleagues. So please stick around outside.